Okay. So this is the homework video for Module 6 acid-base reactions. It's talking about buffers, salts, and neutralization enthalpies. Okay. Getting into the multiple choice, the first question says that which acid or base pair would be suitable for a buffer, right? So question D is the right answer, as they are weak conjugate pairs. The others, this one, they are conjugate pairs, but they're strong, so doesn't form an equilibrium. This is a conjugate pair, but like hydroxide is considered as a strong base. Hydrogen is considered as a strong base as well, a strong acid as well. So A and B are wrong. C is also wrong, so it's going to be D. Question two: which of the following mixture is a buffer? All right, so D is the right answer, as in HOCl and then NaOCl, right? The OCl ion here and then the HOCl ion here, the HOCl molecule here, they form weak conjugate pairs, and then the stoichiometric ratios are roughly. It's not the perfect performancing buffer, but it is a good buffer. Okay, so in contrast to question C, this is like the volume is like 1 and 10. Too much. It's a bit too much. Okay. And HCl is strong acid, so it doesn't work. Question three: a few drops of 0.1 mol per liter of sodium hydroxide is added to a 100 ml mixture containing 0.1 mol per liter acetic acid and 0.1 mol per liter of sodium acetate. The pH of the solution uh, uh, will increase by a small amount. Okay, because we form a buffer with a sodium acetate. Acetate ion is the conjugate base of the weak acid, acetic acid. They are in equal molar, equal concentration, so you are at the best performance. 0.1 mol per liter sodium hydroxide isn't a very concentrated disturbance, right? So it's going to be buffering. Question four: a buffer was prepared using sodium hydrogen phosphate and sodium dihydrogen phosphate. Which of the following equation best demonstrates the effect of the buffer when a small amount of potassium hydroxide is added? So although in class we sort of mentioned that adding an excess base or adding an excess acid into a buffer system, treat it as like an equilibrium shift. All right, so that's like the most reliable way, and then the most beneficial way for you to get marks in the exam, because you can mention LCP and all that. There's an alternative thought, right? Because like if you think about the equilibrium shift, you end up really consuming one of the conjugate acid or conjugate bases, right? So you can sort of treat this as like excess base when introduced into a buffer. It reacts with the conjugate acid, so that the conjugate acid sort of neutralizes any base added, so like it doesn't really change your pH that much. So it's just an alternative view, and then question C will be like that. Okay. If you're keen to know more about this alternative view, let me know. We'll have a look at this during class. Question five: which of the following, when added to 0.5 moles of acetic acid in a 1 liter container, will produce a buffer? Right, so this is a bit tricky question, right? So if you look at all the answers, none of them is a conjugate base for acetate ion. However, if you do add a base to acetic acid, they will neutralize each other, okay? And then one of the products, right, which would be the salt, in this case, if you add sodium hydroxide, you will produce sodium acetate. And then the acetate ion from that can act as the conjugate base, and therefore you can form a buffer. So if you add 0.25 moles of sodium hydroxide, it will neutralize exactly 0.25 moles of acetic acid. You will produce exactly 0.25 moles of acetate ion in 1 liter of water. Therefore, you do form a optimal performance buffer. You don't want to add too much. If you add 0.5 moles, it just completely neutralizes. There's no more acid left. You just have all your conjugate bases. That's not a buffer at all. If you add more than 0.5 moles, such as selection C, then you will just overwhelm it, and then you will end up with a basic solution. Right, same thing with D, right? So barium hydroxide, if you add 0.25 moles barium hydroxide, just completely neutralizes with the acetic acid, because it's two hydroxyl groups. Okay. Question six: which graph correctly shows the changing pH when increasing amount of HCl is added to the mixture containing equimolar concentration weak acid? So you have a buffer solution, Adding HCl, okay. If it's a buffer solution, it will slowly initially buffers that the pH change, and then as soon as your capacity runs out, it's changing pH really quickly. So the correct answer is B, right? The other choices doesn't make any sense. Question 7. A solution containing sodium hydrogen carbonate, so that's sodium bicarbonate ion, and sodium carbonate is a common buffer present in natural water bodies, which roll off the table correctly identifies the chemistry of this buffer. All right, so it's between HCO3 minus and CO3 2 minus, okay? And HCO3 minus acts as an acid, and you have this buffer equation, so it's either A or B. We don't even have carbonic acid, so C and D is just redundant. And so when acid is added, you're increasing the concentration of H3O plus, so you sort of shift left. There you go. So correct answer is A, right? Another sort of like the alternative view, right? I'm just gonna go through it here. If you add acid, that sort of reacts with the conjugate base here, and then sort of gets neutralized. Does that make sense? So it's an alternative view, but I still prefer the equilibrium shape. It makes more sense. The following stimuli is used to answer question 8 and 9. pK values for some weak acid and 25-degree factors. This is following. The student wants to maintain the pH of a particular solution in the range of 6.9 to 7.25. Which of the following acid-base pair should the students use as a buffer? So for a buffer at optimal performance, their buffering pH is equals to pKa. If you're confused about this, have a look at the material right after the Henderson-Hausbach equation derivation. It should be very next to that. And again, so you want to choose a pH that is sort of like in this range. Then you want to pick a pKa that is in this range. So the best one would be the hypochlorous acid. Yeah, there it is. So B is the right answer. 9. A buffer composed of ammonium and ammonia has a pH of 10.3. Which of the statement is correct about this buffer? Adding a small amount of HCl will increase its buffering capacity. Okay. So in terms of this question, we are at a pH of 10.3. 10.3, 10.3, so that's like near the pKa value of ammonia, but it's slightly higher, okay? Which means that now there's more base than acid, okay? So we're not really at optimal level. It's because now the base is slightly more than the acid. Not that much, but it's more. It's not really that little as well, because remember that the logarithmic scales are like base 10, so you sort of like 10 to the power of this instead of just there's like difference of 1. It's actually a difference of 10, right? So 10 times more concentrated. So like, yeah, that would be a big difference. So you want to add HCl so that it neutralizes this 10 times more base. All right, so it brings it to a rather more balanced ratio between the conjugates. Okay, so that you increase the performance. Okay, and question 10. Question 10. So we have a hypochlorous acid, pKa is equal to 7.5, is an active ingredient in the pool. Okay, so this is the pool, okay? It dissociates in water according to the following equilibrium. In a particular swimming pool, the equilibrium concentration of that is 1.5 times more than of that. What is the pH of this pool? Guys, multiple choice, so straight away, right? Henderson-Hausbach equation. You should be able to just use it straight away. Otherwise, you're gonna need to be able to do IC tables and derive for it. It's really complicated. So pH was equals to pKa minus log base 10, like the ratio of the conjugates or something, right? Look it up. So it ended up to be 7.32. Question 11, which of the following chemical species is amphiprotic in an aqueous solution? There it is. B is the right answer. The other A is only an acid, C is only a base, D is only an acid, okay? Well, D is an acid is not because it can donate a proton, it's because it reacts with water to form to form carbonic acid, which is an acid. 12, a student conducts an experiment to determine the enthalpy of neutralization delta H between sodium hydroxide and hydrochloric acid. 100 ml of 0.5 mol per liter of hydrochloric acid was added to 100 ml of 0.5 mol per liter of sodium hydroxide. The initial temperature of both solutions was 25 degrees Celsius. The final mass of the mixture was 183.1 grams, and its final temperature was 29.4 Celsius. Right, so direct applications of MC delta T to negative n times delta H. All right, should be a really easy calculation. I won't show it here, but if you have questions on this, I'm happy to demonstrate in class. Which of the following neutralization reactions would produce an acidic salt? Yeah, so if you have a strong base, if you have a weak base and a strong acid, you produce acidic salt. That's just by definition. There it is. So A is the right answer. The acidic salt is called ammonium chloride. Okay. And then the acidic part will be the ammonia because it's literally acidic, as because of ammonia is a weak base, so its conjugate acid is weak. Hydrochloric acid is a strong acid, so its conjugate base is extremely, extremely weak, so it's not even a base. Question 11. Student prepare a buffer using acetic acid and sodium acetate. A few drops of universal indicator were then added to the buffer. Write a balance the chemical equation. There it is. And I note this equation as equation star for future reference. A small amount of either the small amount of acid or the small amount of base is added. There's no change in color, as in there's no change in pH, right? Because we have a buffer system. Sort of just explain how buffer protects the pH in this question. So make sure to define what buffer is, and then use dot point to answer like what if acid is added, what if base is added. In your question, in your answer, definitely define LCP and then apply to this question, right? I won't go through the details. You should be able to do LCP by this point and then apply to buffers. I will just say that I did acid first, and I did acid in its full glory in terms of definition and all that steps. And then for the sodium hydroxide, again, the idea is very similar. You would use IC table, sorry, not IC table. You would use LCP and then shift this, shift that. It's going to be identical. It's going to be very similar. So what I did is I say something very brief. Okay, it's something like very similar to the previous part. Okay, don't need to be so detailed in the second part when you talk about the base, because you literally talk about definition LCP again. You need to define that again. Okay. Part C, when a small amount of either 1.0 mol per liter of hydrochloric acid or this much of base is added, the color still changes. Now you see the difference here. Before was 0.1 mol per liter of acid or base, and now it's 1 mol per liter, so it's much more concentrated in this case. So your buffering capacity isn't infinite, okay? So it's finite, right? When external disturbance is ongoing, the buffer equilibrium continues to shift in a certain direction. Soon enough, one of the conjugate becomes limited and hence reduces the effectiveness of effectiveness should be E, right? Not A. I don't really care. It's what it is, what it is. In this case, for concentrated hydrochloric acid and sodium hydroxide, it's very likely that you exceed the buffer capacity and then you end up with a big pH change. It doesn't buffer anymore, okay? Question 12, the table shows information about 3 solutions. You got X, Y, and Z. Each of the solutions contain different types of ions, but the ions all have the same concentrations. Okay, so the pH of water in a particular fish tank must be maintained within a range of 6.95 to 7.15. Again, this is the question about optimal buffering pH. Remember that is equals to your pKa. So evaluate the suitability of each of the solution to protect the pH that's required. Well, what you need to say is that define how this works, and because this is not a multiple choice question, you still need to derive for that relationship, right? As in the optimal buffer is pH equals to pKa. It's very easy to derive. Okay, just use the definition of what does it mean to be an optimal buffer. Each unique buffer has a unique pH which they are most effective. This is dependent to their strength. Okay, for an optimized buffer, the concentration of conjugates are equal. We have this is like a general acid, right? I don't have an example, so I just use a general acid HA plus water, reverse and forward to produce hydronium and A minus its conjugate. So the Ka is this. However, we're assuming that we're at optimal, so the conjugates and the acid itself are equal in concentration. So you can straight away balance out those two concentrations and leave behind only the hydronium ion concentration. So the pH is that, which is just pKa, right? If you're trying to substitute Ka with that, you get it. So pH equals pKa is the optimal buffer pH. So with reference to the equation star, right, we can select the suitable buffer based on the pKa value. We want 6.95 to 7.15. The only one that's sort of in the range is Z, right? They are so far away. This is not even a weak acid, okay? So there it is. So X is not suitable. Explain why. It's not even a weak acid. Why is not suitable? Because it protects the pH at optimal very far away from the requirement, and Z is suitable. Okay. Question 13. Consider the following equilibrium system. This is the phosphoric acid, right? Okay. What is the conjugate base for that? We'll lose one hydrogen. You get this. Exactly that. Easy. So question B is easy too. I won't even go through it. Question C, that is an amphiprotic, exponent term amphiprotic, and the answer includes two chemical equations demonstrating that it is amphiprotic. So the question basically asks you to write two Bronsted-Lehrer definitions for this being an acid and this being a base. Define amphiprotic. It means that a substance that can act as both acid and base. Pretty easy stuff. Okay, let's move on. Make sure when you write the dissociation equation, it's reacting with water. People make this mistake for so many times. I don't know why. It's always reacting with water, and then the water is like the substance that you can donate and accept the proton to form hydronium and hydroxide. Okay. Question 14. You have three reactions. Sodium hydroxide neutralizing with hydrochloric acid. This is strong and strong neutralization. Delta H is this. This is strong and strong. But the second ionization of sulfuric acid is weak. You should already know that. If you don't know that, you should already tell that from delta H's, okay? And then question 3 is just a strong and then a weak acid together. Okay, so dot points, explain each one separately. Reaction 1, neutralization between strong and strong. This reaction is simply the following net ionic equation is going through in class, so it's always negative 57.1 kilojoules per mole. Reaction 2, we have a diprotic acid H2SO4. Although the first ionization is strong, the second ionization does not ionize completely. It is very close though. It's kind of like, I don't know, it's 98% or something last time I checked. But it's not a strong acid, okay? So you still need an extra step. So on top of the net ionic equation here, right? Every neutralization has that. But on top of this, if you have a weak acid, you need to force the not dissociated part of this in equilibrium. You need to force it to a completion in a basic condition, right? That forcing requires a little bit of heat input. Therefore, in total, right, this is why it releases less heat, because in this process, it has absorbed a little heat from surroundings, so in total, it's less. You can even calculate how much less, right? It's 2 kilojoules per mole of energy being absorbed. Reaction 3. Reaction 3 is between sodium hydroxide and a weak acid. And just straight away mention that HCN is a weak acid, hydrocyanic acid. Right. So simply an extra step is required to neutralize all of the equilibrium leftovers, right? So and absorbs heat, of course, but this one is because this is a really, really weak acid, so it absorbs much more heat than the second ion of sulfuric acid. Therefore, the delta H is much more significantly towards the positive side. Okay? So there's that. Let's move on. So question 15, we have an increasing amount of hydrochloric acid were added to water and an unknown solution. So water is this dashed line. Unknown solution is this curved line. The pH was monitored. Explain the trend, right? Include relevant equations. So HCl is a strong acid. It is dissolving completely in water and produces hydronium. If it's just in water, this increasing H3O plus will not be buffered, so the pH just directly decreases according to the definition of pH equation. This is consistent given that the plot x-axis is actually in logarithmic scale, it's just not being written as a log, but you can see how the increment is like 10-folds each one. It's secretly logarithmic scale. So it's kind of like pH versus log of something, right? So the gradient is constant. It's going to be a linear relationship. It's going to be a negative gradient as well because of the negative sign. And that is consistent with what we have in the graph. And then the other solution you're supposed to guess, I don't think it's that hard to guess that it's a buffer solution, right? Seeing that the pH doesn't even change this much initially. So in the other solution, the graph depicts the slower change in pH with increasing reduction rate. This would corresponding to behavior of a buffered solution, where in a buffered equilibrium, just generic buffered equation, when you increase acid, LCP dictates that equilibrium shifts the position to minimize initial change. In this case, the reduction or the reaction would shift left to minimize delta pH. This explains the slow change at the start, and as HCl is keep adding, the performance of the buffer system reduces and hence accelerates the delta pH, and that's why we get an increasing changing pH gradient. All right, so sorry about that. Continuation, question 16, describe the importance of one buffer system found in natural system, including at least one relevant balanced chemical equation in your answer. So I've used the human body experiment. I don't know, you can choose any. I just happen to know more about human bodies. There's no particular reason besides I am a human, so I should know about myself, eh? So in human biology, proteins and enzymes in our body relies strictly on temperature and also pH, right? Just by the way, there's also temperature. Temperature is another important factor. So everyday life activities such as eating, exercising, tends to alter the blood pH level. Okay, our ancestors, meaning the ancestors like I don't know, billions of years ago, or millions of years ago, not like the monkeys in the forest, is our ancestors, like the first few animals that went to the land from water. Okay, these are so these ancestors work out a way to sort of balance their pH level. It's like natural selection or something. And then the animals that do not know how to balance the pH in their blood died. Okay, so there's a little biology here. So the system works alongside with our lung and our kidney to try to maintain its buffer always at optimal level, no matter what you do, right? Yeah, but of course, it's like if you drink like a ton of sulfuric acid, right? Besides that, you get burned to death. Like it's still going to override the buffer. So do not drink sulfuric acid, and drink a little bottle of vinegar is fine. Okay, I'm sure that's tasty. Right. So this is our buffer equation. Remember that in human blood is always this carbonic acid. Okay. An easy way to remember this is that human always breathe out carbon dioxide. So carbon dioxide is a natural gas. It's like a really, really normal, common gas in our recycling systems. So like the buffer that would more likely to be formed is carbonic acid. So in this case, just the same thing. Our LCP if excess acid is added, you ship this and ship that. I won't go through the detail, but you get what this means. If you don't, you're in big trouble. Let me know. I'll go through it again in class. Question 17. 100 ml buffer solution contains da 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 da. Okay. Again, they're not really equimolar, so it's not at optimal performance. But the capacity is pretty good. It's 1.5 moles per liter. It's pretty good. Okay. A says that the pKb of ammonia is this much, and show that the pKa is this. Right. Remember the calculation basics, right? So it's conservation relationship. B, calculate the pH of the solution. Well, like it should be just the Henderson-Hasselbalch equation. Like that should scream at in your heart when you do this question. If it didn't, you can also derive it. Regardless, you also need to derive it if you know the Henderson-Hasselbalch equation. At least you know what to do now. IC table, assume small change, yada, yada, yada. Get the Henderson-Hasselbalch equation, substitute the values, and there it is. A difficult question turns to be easy. Question C, the final pH of this after all. So now there's a disturbance that asks you to calculate the final pH. Well, certainly, let's do that. So like from the above, right? So X is the concentration of hydronium ion. Let's just work it out. It should be this number. It's easy to be is easy to work out. Is use the pKa values or the Ka values to solve for X. Okay, is extremely small compared to the amount of sodium hydroxide added. So when sodium hydroxide added, it will first neutralize with the whatever the hydrogen ion that's in equilibrium, but since it's like so like insignificant, right? Which is it first reacts with that, and after this is finished, it goes ahead and reacts with our conjugate acid. But this is so little, we don't even just forget about it. We just might as well pretend it doesn't exist. So we just say that the sodium hydroxide goes straight to react with this. So in your IC table, 1.0 is your initial concentration, take out 0.2, neutralization, right, goes to completion, and then it becomes 0.8. Right, it shouldn't be 0. It should be something like this, but it's too small, so let's just assume to be 0. Okay, and same thing, if that has neutralized this much, and then you will produce your conjugate base because neutralization by this much. Okay, so you start with this, you end up with 1.7, and then whatever X is, you want to find this. I should name this a different symbol, maybe Y or something, because it's literally a different symbol. But I just used X. This is just like I'm saying that if you add this disturbance, what is the new concentration of the hydronium ion? So you can use the Henderson-Hasselbalch equation. You don't need to derive it again. And substitute all the relevant values. You see how the pH is 9.48. This is really not a big change compared to 0.9.33. Okay, if you just impure water, 0.02 mole of sodium hydroxide is crazy. Okay, it's going to rise your pH like up to 13 or something. Okay. Question 18. A gaseous hydrochloric acid was bubbled into two solutions, A and B, both at constant rates. Solution A and B contain same type of cation and anion, and the ions all have the same concentration in both A and B. The pH of each was monitored in this graph below. So it seems like I have two buffers, right? Because the pH doesn't change this much in start. But solution A seems to change faster than solution B. So sort of it runs out of its capacity more quicker. So solution A and B are both buffer which contain equal concentration of the acid and the conjugate. The buffer system is given by the following equilibrium. This one, generic. And then at T0, the pH of the buffer is equal to pKa, right? So roughly 4.8. By the way, a pKa of 4.8 is exactly the acidic acid pKa, okay? So I'm presuming that this is the acidic acid buffer system. Right, so of the weak acid, as the conjugate are equal in concentrations, as gaseous, this is bubbled, you produce more hydrogen ion. That's pretty standard stuff. So hydrogen ion increase, equilibrium shift left, yada yada yada, LCP. Okay, so it minimizes the change. And at T1, solution B's pH is decreased more than solution A's pH, is because that the buffering capacity is lower than that of the solution A. Right, it has to be because we can't explain the otherwise. The buffering capacity of the solution decreases HCl bubbled through due to the decrease in concentration of the conjugate base. Right, just keep running out of conjugate base, and you run out of being buffering, being an optimal buffer. Okay, it just happens that solution B is more capacitated, there's more concentration of all the conjugates, so that you can buffer more. So sample answer, you can pause here to copy, and I'm gonna move on. Question 19. Carbonic acid and hydrogen carbonate buffer plays an important role in regarding the pH of human blood. Carbonic acid ionizes in water according to the following equilibrium. This one. So the equilibrium constant for this is this. For normal human, the pH is 7.4. Cellular respiration produces carbon dioxide, yada, yada, yada. What will happen to the hydrogen carbonate concentration if cellular respiration increases during exercise? So if respiration increases, more carbon dioxide is produced. So by LCP, equilibrium shifts to minimize the initial change, and hence more carbonic acid will be produced. Now, in the first equilibrium, as more carbonic acid is produced, you will shift equilibrium forward to produce more bicarbonate ion. Okay, it's a very nice equilibrium relationship. Question B, so the normal concentration of hydrogen carbonate is this much, and then the maximum concentration is this much. Assuming that the pH of the blood remains constant, calculate the greatest amount of moles of carbonic acid that can be added that doesn't exceed the levels of the kidney. So you know that the maximum allowable is this much. All right, so just sort of make sure that this finally is this much. You start with this much, okay? And you need to add by 8 to the power of 10, 10 to the power of -4. So this thing, whatever initial is, I don't really care, needs to subtract by this much, okay? And then we end up getting some X value. And then we need to maintain the pH at 7.4, so that's the hydrogen ion concentration. I don't care what's the initial, okay? Only the final state matter. So we can solve for X, right? We end up with X equals to that. But this is at equilibrium. This is not how much we add, okay? This is how much we produce in the initial system. So if you reverse engineer X and calculate that, you get this much. So that's the maximum amount. It's allowable for you to have in your body before you get sick. Make sure to convert into the moles because it's asking for moles, so C times V as well. Question 20. So a student performed an experiment to investigate the change in temperature during neutralization between hydrochloric acid and sodium hydroxide. Tells you the amount of hydrochloric acid, tells you the initial temperature. It tells you we have 5 grams of solid sodium hydroxide is added, and then the heat capacity of the mixture. Right, so then show that the maximum temperature is this much. So we want to consider the generic equation where sodium hydroxide reacts with hydrochloric acid to form this and that, this much, and then label 1, 2, 3, 4. So the left-hand side, we want to calculate who is limiting in order to figure out how many water is formed, right? So left-hand side, so sodium hydroxide is a mole of 0.125 mole. Hydrochloric acid is 0.08, so hydrochloric acid is limiting in the sense that now there's 2 different heats, right? There's a heat where you dissolve sodium hydroxide. It goes like this, okay? How much of sodium hydroxide has been dissolved? 5 grams. In terms of moles, that's 0.125 moles. So how much heat does that produce? Multiplied by this, okay? So that's Q1, which is this much. And then there's also the heat produced from neutralization because water has the same mole as hydrochloric acid, so just use the same mole, multiplies by the molar enthalpy, and you get that, okay? Now, if you add up those heats, that's the total amount of energy being released during this process. Okay, and it's equals to MC delta T. Delta T is final temperature minus initial temperature. Rearrange for your final temperature. Make sure to use Celsius for the temperature. You could also use Kelvin and you can subtract it back. Doesn't matter. You will end up with the right answer. Okay, 73.7. Okay, question B. In the experiments, the students reported a maximum temperature achieved by the solution to be this much. Why is the experimental value lower than the calculated value in part A? Well, there's always energy loss, right, in real life, right? Surrounding temperature is always lower than 70 degrees unless it's on Venus or something. Right, so there's always a constant flow of heat outward, and therefore you lose a lot of heat from the combustion to the surrounding, and then therefore you decrease the amount of temperature that you can rise for that solution. Okay, so pretty much it. This is the end of this homework. I'll see you next time. Enjoy chemistry and physics. I'll see you next time.